Hey, so this is the second part of the Chapter 5 notes. And this is supposed to be, say, 5.2, not 3.2. I don't know what happened. So that's supposed to be 5.2. And I don't want this video to confuse people or to make them have to think too deeply. This is more for if you really, really are trying to follow and really want this deep understanding of what's going on. I'm going to give a little explanation of it. If not, the summarization for you is that on this first page, you need to make sure that you know that a key thing is that you overlap the shared electrons. You need to know that there are 2 electrons in the bond. You absolutely have to know the bond length and the bond strength stuff. You have to be able to look at a molecule like I did in the last video and be able to identify which are the sigmas and which are the pi's. You need to make sure that you remember without a doubt that the pi is only the second part of the bond, and that has to start with a sigma. You also need to know that there are 2 things that affect overlap. It's the distance and it's how they overlap. That it's much better to do end-on-end overlap than some kind of weird sideways overlap over here. That's not good. And then the last bit that we were talking about was the look of sigma bonds. And I was saying there's 3 different ways you can have them look. So your sigma can come from, in this case, this was an s orbital because hydrogens have s orbitals. They each have 1 electron in them. And when they overlap, the electrons can jump into each other's orbitals and move around really fast. That's one look. Another look is, again, the s orbital here overlapping with a p. And he had an empty space. That's what the overlap is going to happen between, is the hydrogen's 1s. And then the chlorine's empty space over there. And then the last one was 2 chlorines because they both have that empty space and they can overlap. So keep it was that you have to have, if you're going to overlap orbitals, for you to make a bond, you've got to have an empty spot to be able to do some overlapping. If it's full, it's not bonding because there's no reason to share because it's full. That's why the noble gases don't like bonding. And then I had left the last one with just a little bit of a question of, we have some issues here with beryllium because he has 2 electrons. That's great. We know this molecule happens, but how on earth are we going to have a bond happening when beryllium is happy? But we know in lab it does, so it's like a conundrum. And then over here, look at the electrons. What's the problem with B making 3 identical bonds? Well, again, the s orbital is full. And then the p orbital, it's only got 1 opening. And then for the CH3, the big issue was that this one has, again, the s orbital is full. And it has 2 p orbitals, but you need 4. But of course, there's no such thing as 4 p orbitals. How are you going to make this happen? That's the question we're asking. But here's what goes on. This is what beryllium looks like to start off with. He's got an electron here and 1 here. And so the first thing that everyone said was, oh, hey, he's got 1 there. So what must happen is that this one, the one that was right here, he must not be there anymore. He must just pop on up to that p orbital when he's doing bonding. And everyone's like, oh, hey, that would work because then there's some space. So look, hey, this one could do a bond and this one could do a bond. Maybe that's what happens. And so they say the same thing would happen with that beryllium example. So the boron example where the boron's in the middle. And then oh, yeah, that would work. You got to do that for the hydrogen example too with the carbon. Now, before I go any further, I want to point out one thing. If you look up linear on the very last page, so that guy's linear, and if you look up trigonal planar, and if you look up tetrahedral, so again, I'm going to go to that last page. Let me go. Oh, it's not letting me go. Oh, no. I'm now frozen. Okay, it's working in. Sorry, that's crazy. All right, so if we go to that last page at the end here. Oh, I was saying, hey, beryllium. Here's a beryllium compound right here. Remember, so he's sp. Keep that in mind. Notice the trigonal planar is sp2 and tetrahedral is sp3. So sp, sp2, sp3. Keep that little phrasing in mind. I'm going to go back on up. So hey, look, I have an S and a P. And if you remember, this one was supposed to be SP. Okay, there's more to it than this. I'm just pointing something out. And then look, this is SP2. And this guy is SP3. Like you can look at that table. Okay, so that's great. They're all like, that's awesome. So probably what happens is that this is some kind of like an S bond overlap. Whereas like this one over here, you got the S bond, but then beryllium, he's got an electron in his p orbital there, and then like an electron on the p orbital there. But you know, one of the electrons is an S. Well, the problem is that they looked up all those bonds and they found out that all those bonds are actually identical. So shifting one electron isn't enough. The bonds from the central atom have the same length. They're identical. So you can't have some p's and some s's. They have to equalize so that all the valence orbitals combine parts. So this is supposed to be our example of what happens for BeH2. And I do think this is kind of some interesting stuff. It falls apart when you get to really huge molecules. There's another theory that comes into play then. But it works for small molecules, and that's what we're focused on in G and Chem. So check it out. This is what beryllium had. Again, all this hybridization stuff, it's all just the central atom. We are not messing around with the outside atoms. So remember, he was, what we said was he was originally 2s2, but we jumped one of the electrons up. So we have an electron here, and then I got an electron in one of those two parts there. Notice that I'm not even talking about these guys because they're empty. They're not involved. So what they said is, hey, so what must happen? They must kind of mesh together and then kind of magically come out as some kind of combination. And that's the best explanation I can give you guys. So if you imagine like half of him being combined with like half of him, you get these two pictures. The key bit on this, and this, I know it seems like a little bit of hand waving at this point, because I can't get too deep. But the key thing on this is that you started with 2 orbitals and you still have 2 orbitals, but now they look the same. This orbital is like half S and half P. That's a little messy. So this orbital is half S and half P, and so is the other one. Crazy cool, right? So now we have a reason for why each of beryllium's electrons can each bond in the exact same way with a hydrogen. And remember, the hydrogen doesn't change. The hydrogen has 1 electron. It's like a sphere shape, so he hasn't changed. So let's just take a quick look at the other 2 guys. I don't want to get overly focused on this because this is more understanding. You will not have to figure out on a test how many this or that. I mean, you're not going to have to figure out that it takes 1 S and 2 P's because you've already got that chart to tell you what it does, right? But in this case, remember, we kept the 1 electron and we bounced, and we had one up there already, but we bounced that electron up. So notice we have an electron here, electron here, electron here. So now we're splitting into thirds. So this is like a third S and 2/3 P, because remember, they all mix all up and then they spit back out the same number of orbitals because we need those orbitals to be identical. We need 3. And we had 3, the way we drew it up here, we had 3, but they weren't identical. So now what we're basically saying is it all averages together, a little bit of each of them average together, and each of them are like a third S and 2/3 P. But so we're not looking at fractions and everything. We just call all of these SP2. See, a third of S and 2/3 P, but that's all called SP. And then last one, remember we bounced the electron up here. So we had an electron here, electron here, electron here, electron here. And so to make these 4 bonds all come out the same, you have something that's a 4th S character and 3/4 P character. So a 4th S and 3/4 P. So now you understand. Now I know that you understand. Now you can forget everything that I just said because you've got the chart. This is kind of saying the same thing as that other chart at the end of the page also says. So if you're SP That's that linear. This is your electron geometry. Remember the electron geometry? That's the easy one. There's only 6 of them. So if you know this is the electron geometry, this is what you got. You're going to have a total of 2 sp orbitals. One's going this way, and you kind of can't see his little tail. And then one's going this way, and you kind of can't see his little tail. And again, another atom like a hydrogen could come right in here and bond and make a nice, lovely little single bond, sigma bond. It'd be beautiful. Alrighty, now we have sp2. And again, you can't quite see the tail on these because they all kind of cover each other up, but they all have like a little bit of a tail. You just can't quite see them. And again, trigonal planar. sp2, you already know these degrees. So this one has a total of 3 sp2s. This one has 4 sp3s. Now this one, it's crazy. You're like, okay, so where'd the D come from? Well, this and this is mostly the third row and down. And they all have d orbitals. And our little hand waving thing we say is we're like, oh, well, there's d orbitals. They're really close by. So those get involved with the mixing. And that, it does work. It's an explanation that works. So that's what we're going with. So sp3d, it just means that some of the d orbitals from that guy got involved. And then this is spd3d2. So again, just if you want to just memorize those, you'll notice they all have kind of a similar-ish look. They all basically look like lobes, right? You need to know how many there are. You would want to know that. Oh, and I'll tell you one more thing too, is so regions of electron density 2, and notice that there's 2 letters, a letter and a letter. And when there's 3, a letter, and then 2 letters. So there's a P and there's a P and a letter. It carries through like that. So there you go on that. And this is just more emphasizing this, that when we were saying that there's a total of 2, what that means is that you have an electron in each of the SPs. And then when there are 3 for the boron, so we're carrying those same molecules all through this whole thing, we have 3 SPs that each have an orbital, an electron that has room. He can do bonding, and everyone's happy. And the same thing goes for the CH4. So just as our little review, more Newton comments. Again, I've got little comments in there for you. So single bonds are sigma bonds that form. And so you could either have an SS, an SP, a PP. Those were all on the first lecture or the first session. Or you can do something that's hybridized middle with an S or a hybridized middle section with a P. Meaning all these guys are hybridized. And they could either have S's all on the outside like that, or they could all have P's all on the outside. You know, that they could do like a P overlap. You kind of see that. Again, the outside atom doesn't change. It's just that middle guy. So the central hybridization is, the central carbon hybridization is sp3, and it has 4 of those to bond with this guy. The H's are bonding with s orbitals because they're on the outside, and they have empty space. Like their S's, they look like that. It's a 1s. He's got plenty of space. And then the second one, the central hybridization on this guy is still sp3. It has 4 of them to bond with. And these chlorines are just like we talked about before. So he's got his crazy looking hybridization look going on. This is the carbon. But the chlorines, they're just doing their little overlaps on the edges with their little P's. And they're good to go. And they overlap with the hybrid orbital longways. Then, and I'm going to just finish up this section. It'll be just a little bit longer than 15 minutes. Then we have multiple bonds. We have pi bonds. So this is what you need to know from pi bonds, is that you just need to know that pi bonding is when 2 electrons are, and remember, this is all covalent, so they're all shared in a bond. And they overlap the, they're all shared in a bond, blank and blank, the planes. Oh, I'm sorry, above and below the planes of the atom. So here's the thing. If you got a bond like this between 2 carbons, like there's 2 electrons here, they're taking up that space. You can't like You can't fit any more than 2 in there. Even though we'll draw like a line like that, those 2 electrons aren't actually very close to the 2 that are making that sigma bond. So we have this thing called unhybridized orbitals. That's the word I meant, was unhybridized when I said non-bonding earlier. Unhybridized orbitals overlap to form pi bonds. So remember, this was what's going to happen is that he's got a p orbital that's not doing anything, and this overlap is going to look weird. We call it one overlap, but it is kind of like the top and the bottom overlap, all right? But we call it one overlap, even though I know it looks like 2, and I'm sorry. But when we're saying it's above and below the planes of the atom, it's because the sigma is already stuck in the middle right there. And so the second part of the bond can't be there. This s orbital and this s orbital, of course, they don't have any density in the middle of the bond either, but it's an up and a down. And again, this would be 1 sigma and 1 pi, even though I know you're seeing the extra lines. We call that 1 pi. That's what happens. Those electrons can move all about, boop, 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 all about, but they have to stay in the above or below. And they don't form hybrid orbitals. It's just the sigma stuff that does that. The empty piece don't do hybrid orbitals. They all have a sigma framework before forming. And so the first bond, the first pi bond, that's going to come from the central atom and the p external atom sideways overlap. So what we're saying is that it's not like this. Before we kept talking about how the p's overlap like that. That is a sigma bond. These guys are overlapping sideways. See how it looks sideways? Like they're up and down, they look sideways. Those are sideways. And if we had another set of p, and this is where it gets really hard to draw, but if we had another set of p's, boop, boop, they're going to be behind. That's behind and in front. It looks kind of crazy. And I can't figure out why I put this in here like this. The first pi bond. I would just say that it forms from the central atom and the p overlap. And that's how it happens. So I wouldn't stress about understanding this. I wouldn't even stress a whole lot about understanding this. Know these words, above and below. Know the pi bonding is above and below, and just know that they are unhybridized orbitals. That's what I would make sure I knew. And you're going to be good. And this is just the lastest, littlest of bits. So double and triple bonding with carbon atoms come from the carbon atoms unhybridized, this is just a review, orbitals. And if you look at the comparison regarding the electron positions in the carbon atom, that is sp2 versus sp3. This is the sp2. Remember, he had 3 of them, and look, the carbon had an extra spot. But this is sp3, and there were 4 of those, so there's no empty spots left over. When there is an empty spot and there's one guy in it, this is the guy that can do double bonds. And again, we have a quick little picture. So if anyone ever showed you a picture like this, so this is the overlap of end-on-end overlap. So this is a sigma bond, and these guys are overlapping end-on-end. Those are sigma bonds, and these are sigma bonds. So notice this first picture, it's all the sigma bonds. Then, notice that we have like this little pi thing. This is the leftover spot, and those are that sideways overlap. That's the look of it. And if you were to really try to see a set in front, a set in back, and above and below, it's right here. You don't even have to know all of these, but it's interesting if you want to read about it. You'll notice there's only a few learning objectives for this whole thing. You need to be able to tell the difference between these ones in terms of the nature of the overlap. That also includes things like single, double, and the length and the strength. Length and strength. Notice that we're still talking about covalent bonds when we're using this theory. Remember that it's orbital overlap that makes that bonding pair of electrons happen. And you need to be able to identify, if you know the molecular structure, what the hybridization is. So easy peasy. And don't forget, you've got this super awesome, wonderful chart here to help you with anything you might be wondering about. And I'm going to change this word. I'm just going to take that word out, the non-bonding. This one is non-hybridized. And this is non-hybridized. All right, I'll leave you be.